discussions or informal discussions in the afternoon. So we will now start a mini course on an important set of exactly solvable theories, on these fishnet theories, and Enrico will give 2 lectures on fishnets.
Tá. Sim. Certo? Okay, so thanks for the introduction. And right, so in summary, I'm going to introduce fishnet theories. In practice, I will speak about fishnet theories as theories made of integrable Feynman diagrams, and so what is an integrable Feynman diagram needs to be defined. And I will do that with reference to exactly solvable spin models, essentially. Then I will provide examples in some specific dimension and with some specific, on some specific spin lattice for a Lagrangian formulation of these theories. And finally, today I will discuss some computation that one can do in fishnet theory in order to compute, indeed, solve conformal data in these fishnet CFTs and related aspects to the CFT part, that is, for instance, properties of unitarity, lack of unitarity, solution of the mixing problem for the matrix of anomalous dimension, and so on. Whereas tomorrow I will concentrate more on quantities which are the multi-point, multi-loop fishnet integrals, which are also quite relevant for Bootstrap in n equals to 4, but they constitute a toy model even beyond that. And how the spin chain integrability applies in order to formulate an hexagonalization program from first principle by means of a separation of variable in the case of disk fishnet integrals, where these words will be better defined. Then we could also discuss, if there will be time, some extras, like Youngian symmetry, which is also very relevant for a Bootstrap approach to the computation of n-point multi-loop Feynman integrals, and beyond, in fact, beyond. Some comment that I would not like to forget, since before in the previous discussion there was a mention, in the previous lecture by Simon, there was mention about conformal symmetric Heisenberg magnets. Well, we are still dealing with this type of spin chains. In fact, for the D equal 2 situation, I will deal with the same type of magnet that Simon was explaining in the Regge framework. And also the Pedro's question about what happens if you, instead having a periodic boundary condition set up of the previous talk, but you rather have some charges at infinity are in 0, minus infinity, plus infinity, well, that would map precisely the Heisenberg conformal magnet to the one that we can solve for computing disk fishnet. I just wanted to mention this, even if it's for tomorrow, because your mind is more fresh about this type of question. You just heard those. So let's go and define what is an integrable Feynman diagram, or at least give our definition. So I'm just picking a graph. Okay, so a graph has a collection of vertices and edges. Okay, so I will have many points on the plane, and some of the pairs are connected by edges, some other not. Okay? In general, this graph will have some topology. It can be planar, it can be non-planar, and by planar versus non-planar, I mean that I can draw it on the blackboard without intersection of lines, without intersection of edges. This is non-planar, right? And so, for instance, P and Q are 2 points belonging to the set of vertices, and it is the case in this particular graph that there will be a PQ edge. Okay? Not all the pairs have edges. And now I'm going to put some excitations in the various vertices, like you would do for an Ising model. If this would be a chain, simply a chain of nearest neighbor vertices connected by an edge PP plus 1, say, I would associate to it an index which is plus minus 1 or 0 and 1. In general, I could have, let's say, higher dimensional representation if you want. So this, the vertex of the index of the excitation could take more values. And if we speak about spins, we generally consider a discrete set of values, say 0, 1 to IP max. Okay? IP max means that the maximal value of the excitation in general will depend on the site. Okay? I could have, for instance, different representation of SU2 in the different sites. So I'm going to define this Ising-like, or Ising-like spin system on a lattice, and I want to introduce integral Feynman diagrams precisely in this framework, because it is a framework where exactly solvable models of statistical mechanics were very much developed before the integrability in Engage CFT. Okay. Okay. In general, let's give an energy to this system. The energy depends on the value of the spins, and okay, what can you expect is quite in generality. You can have some external magnetic field plus, and what matters mostly for us, an energy related to spin-spin interaction. Okay. Notice again that the energy due to the self-energy or the energy due to the interaction with an external field will depend on the site in general. As well, the dependence on the edge is explicit in the edge interaction or spin-spin interaction. Okay? So, yeah, this is quite a general framework. It is very interesting to study in general for this type of system when do they become exactly solvable by means of integrability, because here we have an interaction, right? So interaction generally are something that break integrability. Okay? This system would be a system of particles in an external field, that's all fine, but interaction is very hard. That preserves integrability. We want those cases where the integrability is preserved. So the last thing I have to say is, you see, not all the points are the same in this graph. And even consider a very much larger graph with many more vertices and many more edges. It's useful to separate and define what are the points in the bulk and what are the points in the boundary. So to define a bulk and a boundary. Okay? In this way, I will complete the definition of the system and be able to define a partition function that will indeed be, in fact, be the next step, the Feynman integral. Okay? So, for instance, I may call L a vertex in the bulk, K a vertex in the boundary, and a partition function, which depends, of course, on the features of the graph, but also on the configuration of its boundary points, is, well, the summation of all possible configurations of the bulk for fixed boundary and h e to the minus beta h il ik. Okay? This is very, very standard after all. Now, no, we don't connect points to itself. In
And
fact,
also not the 2 points being connected by more than one line?
it's irrelevant topologically here.
Okay, I see.
Yeah. What we can play with is the strength of the interaction on a certain edge. So if you want to have a twice stronger interaction, you are going to change the interaction at the level of the Hamiltonian, I would say. Okay. Right, so the Feynman diagram is this. In which sense that if I have a vertex, now instead of a spin, the value of a spin becomes non-compact. Okay? And actually, right, for a vertex, I associate a point in d-dimensional space. This is the first thing. Secondly, I give another constraint. Let me ask the graph to be planar. I want only to work with planar graphs. And third, I'm going to tell you explicitly what is H. So for us, we generally, we want to work with an integrable model. So think about XXX, XXZ. We don't want an external magnetic field, all right? So we want just an interaction, which is very non-trivial to make it integrable, as I was mentioning. But now the Hamiltonian, the energy of the system, is going to be a sum over all the edges of a certain delta, which is the strength of the interaction, but in fact will be a scaling power, a scaling behavior in more conformal symmetry language, and times the logarithm of the Euclidean distance. In this case, I'm considering Euclidean. Okay? If you do this substitution, this becomes the integration over the coordinates of the points in the bulk. Okay, so now all these vertices will be points embedded in RD times for all the edges, okay, all the edges, 1 over xp minus xq 2 delta pq. Okay, so sort of massless generalized free field propagator in any dimension. Okay, I'm still general here with D. And this is a Feynman integral. You recognize it as a massless scalar Feynman integral of propagators with this generalized scaling. All right, now what does it mean for this partition function to be integrable? So for the Feynman diagram to be integrable. To be integrable means that we have to find a lot of symmetry in it, such that there will be equations that allow to compute, for instance, exactly this partition function for different sets of boundary conditions. Okay? So about symmetries, well, first of all, there is symmetries by translation and rotation of this object, okay, depending only on the distances. And then we can impose something more, scale invariance, which is not guaranteed so far, because given a vertex, say P, considering here, for instance, a vertex with the valency 5, okay, so the condition of scale invariance tells that the sum over the edges ppk of delta ppk should be equal to the dimension of the space-time. Okay? So this is a first constraint. And this first constraint already allows to introduce a dual picture based on the conformal symmetry at this point, on the scale invariance, which is so-called medial in the statistical mechanics spin lattice system literature, also known as Baxter book. It's called, and related, it's called medial graph or medial lattice. Okay. So how to draw this dual picture? You have a vertex. You are going to draw a polygon around that vertex, connecting the propagators that are emitted from here. Okay. And imposing that these external angles, okay, if this is the external angle alpha, well, alpha, let me say alpha p pk, okay, because it's relative to a certain edge, okay, is equal to 2 pi over d delta ppk. Now, this linear relation translates the scale invariance in coordinate space with the geometrical condition of having a polygon. You wouldn't close the polygon if the summation over delta would not be d. Okay. Nice. This is already something, but it's still not integrability. It's way far from integrability. What is missing is the Young-Baxter. So in fact, when I say Feynman integral, which is integrable, I cannot really say that this is the most general definition of integrability for a Feynman integral. I can't exclude, in fact, that there are Feynman integrals with more complicated topology than the one I'm studying here that can still be computed exactly by somehow integrable magnets, relation to integrable magnets, but they are not falling in the class that I'm introducing now. So it's a Young-Baxter integrability, okay, something more specific. Okay. And this condition is the fact that the medial graph is made only of straight lines. Okay. Okay. Take these straight lines. These are lines on the plane that form certain set of angles at their intersection. And you see I have only straight lines. I never interrupt it. And the associated Feynman integral, at least this you can consider as a portion extracted from a bulk of a large graph, well, can be constructed by the opposite procedure. I insert vertices alternatively inside the faces of the medial graph, and I connect them with the edges, which we can also call at this point propagators. Okay. This property is not obvious at all. Okay. Consider, for instance, I mean, it's not included in the requirement of scale invariance. Consider, for instance, a portion of a Feynman diagram with the topology of a Kagome. Okay. Why topology of a Kagome? Well, Kagome is quite often appearing object in statistical mechanics spin lattices. And is also an object, topologically, as a Feynman integral, is also interesting for, in relation to n equal to 4 super Yang-Mills, in some sectors, in fact. And I'm not going to explain now why. But the medial graph of this object is clearly not of this type. If we impose scale invariance, let's say we are in 4 dimensions, the scaling power of all the edges is 1, therefore all the vertices are, in fact, have a dimensionless coupling. Okay. And drawing the medial graph, you are going to obtain something like this. No. Okay, so now here it's going to be, yes. More complicated, yeah. Okay, so there is no way that you can make straight lines with this configuration of vertices. And this is actually one of the open problems in some sector of the fishnet theories. That not the most general fishnet theory by which we consider to be integrable due to the relation of n equals to 4 has graphs of that type that we cannot make sense of. But indeed, I will not speak about those theories today. I will just consider the more basic no, what I'm saying, what I'm saying is that if you consider a deformation of n equals to 4 in a planar limit and a strong deformation limit with respect to their charges, which we would consider to be the most general fishnet theory, say, with including also fermions inside, there are sectors. That contain Feynman diagrams of this type. For instance, they involve the 3 scalars of n equals to 4 at the same time, which give you precisely a graph like that. And they are already chiral, non-unitary, planar, and conformal theories, for which we know integrability, or we believe integrability by argument of deformations of the quantum spectral curve. But we cannot make sense of this topology from a nearest neighbor Heisenberg model, which is Yang-Baxter or star triangle. Okay. Okay. So the claim of integrability, Yang-Baxter integrability, being related to this property of the medial lattice needs to be substantiated. And here it is. So if you have a set of lines, let me take the simplest polygon that I can build with straight lines, the triangle.
That color is not ideal.
It's not ideal in general, or is this special marker?
That's better.
That's better. I can rather substitute with the blue. If you distinguish well the color from far away, it's clearly different from black, right? Is it?
But the new red is also good.
Okay.
Proper red, both are good.
Perfect. Very good. So, yeah, let's consider the simplest setup. So the simplest polygon that can appear on the medial lattice. The scale invariance condition, I mean, a property of this medial lattice is that lines can be moved across vertices. Okay. This already starts looking familiar to people doing Yang-Baxter, factorized scattering. But in my picture, it means something very specific, right? Here I have a vertex of the associated graph and 3 external points. Here, I consider them as external points, okay, which bear the continuous spins x1, x2, x3, if you wish. And moving the line, this line, let's imagine that I'm moving this line just by translations. I cannot rotate because that would change the angles and therefore the power scaling and the strength of the interaction, the spin-spin interaction. But just by translation, I can move it across this edge. Okay, so now I have the same two lines, A prime, B, and B prime. But the line CC prime has moved across the vertex, the medial lattice vertex. And if I draw now the associated Feynman integral according to that rule, what happens is that a star, what we call a star, that is a convolution of three propagators, has become a product of three propagators. So actually the convolution of three scalar propagators under the condition of scale invariance of the vertex is easily computed times, in fact, a very simple constant factor. Okay. Well, this makes transparent the fact that, imagine that you have an integrable Feynman diagram, so a Feynman diagram of this type, moving line across the vertex, you can relate many different quantities between each other, and therefore define a lot of symmetries. In principle, this type of symmetry allows you to compute directly, even, to bootstrap some of these Feynman diagrams. So in this sense, I have to be more precise and give you some examples. But before that, I would like to write down this relation in quantum mechanical operatorial form, because this allows to define the corresponding Heisenberg spin chain, which was mentioned in the previous talk. Okay. All right, so in general, let me use this notation. Okay, I write one of these generalized propagators in this way as a line, and the delta simply means.
Sorry, can I ask a question? Do like UV divergences ever enter in your discussion?
I guess the Liang. Ah no, Petr.
It's me.
Sorry.
Do the UV divergences ever enter in your discussion here?
This is a very good. This is a very good question. The divergences depend on the boundary conditions. But if you have right, that's a good question. Yeah, I would generally say that depending on the boundary condition, you can distinguish cases where you have divergences, where with cases where you have, for instance, a regular lattice, and you don't have to care about them. But the general answer is yes, you have to care about that.
So what do you mean by boundary conditions?
Boundary condition in the term of the spin lattice system. So what are the points that are integrated in this Feynman diagram, and what are the external coordinates? Okay.
Bring all legs together.
Yeah, bringing legs together may, not always, but may give you some divergences.
But even, I'm talking about divergences that you get when you integrate over these internal vertices. In particular, you use this identity, which is true at the level of, if you do this integral over 1 point, that's fine. But my question is this still true if you take all the possible divergences into account?
I'm not sure I heard.
Sorry, so let me try to be
thank you.
louder. I'm worried about the integration over internal vertices. You could have a graph, right, so I don't know, maybe somehow it doesn't happen here, but you could have a graph where, these are loop integrals and there could be divergences. That's correct, no?
Yes.
And so I'm asking I don't see how this is related to the boundary conditions because you instruct us to integrate over these internal vertices, and that just might be divergent.
Right, so
But sometimes you just need to dimensional regularize. So delta is just whatever, like 4 plus epsilon. And if the relation holds for 4 plus epsilon dimension.
Yeah, but then you
can
break.
No, that
all,
is wrong.
But then you break all this scale invariance conditions.
Exactly.
Yes, this is true.
You cannot dimensionally regularize, indeed. Let's say that I will compute quantities that are well defined. You may have certainly problems when you hit, for instance, specific scaling dimension, but the safest way to deal with these integrals is in terms of analytic continuation in the scaling dimension. For instance, you go to the principal series. That's the safest setup you can think. And it's the best also to define the integrable spin magnet and to produce separation of variables, generally. So that's how I would approach the problem.
But when I was meaning about dimensional regularization, is something that happened, for example, in our paper when we were looking at kite integrals. Kite integrals are divergent. It's true that you can use a uniqueness relation, so star triangle relation up to some point, and then after it, you can introduce the regularization in delta, and then you can expand in epsilon. And then you can, this is scheme dependent in some sense, but at the end, since the answer is not scheme dependent, you can regularize at some point.
Right, but those are divergences that are due to the boundary conditions. So the fact that you are putting legs together and you are collapsing things and making them explode.
Yeah, this divergence indeed is coming when you are gluing two of the legs.
These are UV divergences, like taking an OP of a 4-point function into a 2-point function. All right, so that's expected, and actually it's good that it happens, so we can extract data. Right, so now, long story short, this relation can be written in this way. It is an operatorial relation of quantum mechanical position and momentum. Okay, so you see it, right? Of course you don't. And the reason is that I didn't define p square. Okay? P square of alpha is a fractional power or real power of the Laplacian, right? Here the definition of fractional derivatives of fractional differential operator is not unique. The one I'm going to use here is based on the fact that I assume the possibility of doing Fourier transformation, which of course partially answers also your question, right? Fourier transformation should be well defined. I should be in the space of L2 functions, right? So principal series seems to be the right framework to work with in general. And in Fourier space, the operator is multiplicative, and so I can certainly define a real power of it. Okay. Excuse me? I can't hear. Yeah. There is a typo, but I don't know if it's what you were saying. You were saying this?
I'm saying, do you want the exponent on x to be 2 alpha plus 2 beta? Or just alpha plus beta?
Right, correct. Thank you. Okay. All right. So what is a fractional Laplacian is an integral operator given by a certain kernel. The kernel depends on the power of the power alpha and on the dimension of the space-time. With this definition, you can regard these propagators either as x to some power, okay? So, which are acted on by integral kernels, which are also propagators. So convolution of propagators can be always expressed as combination of p squares and u squares and x squares. With this relation, one can build a universal transfer matrix which solves the Young-Baxter relation.
Can you say how it's related to star triangle, like what is x?
Yeah.
Which one is x?
Ah, okay. It's an exercise for the afternoon. I gotta give names. On the left-hand side, so this is the left-hand side, and this is the right-hand side. Now I'm saying this. Okay. This is just renaming to match the notation. I'm using 1, 1, and 2. So the left-hand side is precisely p square, p on coordinate 1 to the power 2 alpha, which is applied to the propagator x1, x2, so it integrates in coordinate 1, and coordinate 2 is external, so x1, 2 alpha plus beta. And finally, but it also multiply another p operator, so here I left the kernel with the open variable y. It is this variable y. It's like acting on a delta function, if you want. I'm writing the kernel instead of writing the operator. But here, in principle, this line could be integrated and convoluted with a second function. So this is P1 of 2 beta.
So it's identity between operators, sectional functions of one variable.
Yeah, these are operators. So x1.
But then which one is the kernel in variable and out with x3? So
I have 3 because I have 2, but here put any function, any test function here, and integrate it, okay? If this point is y, I multiply by 5y and I integrate over the point y. But I can put a delta function and fix this external point to x3, x4, z, whatever. It's okay if I put here a delta function in point y1. X1 minus y1, say. Okay, so the left-hand side would be this, and the right-hand side, well, you have x1, 2, which multiplies something which would be integrated here, right? Now, we decided that we want to integrate against the test function, so it's a p. Which multiplies, but at the same time, you know, it multiplies the function phi, but also the x2, x1, because this is the space 1, right? This is the space 1, space 1. So this coordinate, it's integrated x1, that's why we were calling it y1. And so it multiplies another x1, x2. P multiplies x1, x2 and the test function. So here we have x1, 2 to the power 2 alpha. This is the explanation put in coordinates. Okay. Right. Is more clear? It's not hard derivation, actually. It's really having an equation between two operators applied to test function. Apply it to the delta function, and you write down with this formalism where 1 over square distance to delta is this line, and that's the picture you get. Somehow you don't agree, but it's simple.
Not just P is integrated kernel, right? So it's in the right-hand side there are double integral, I see, because P is a integrated kernel, and the left-hand side is also
One integral only. Why? Right-hand side, one integration, left-hand side, two integrations. You see that here there are two integrations and here only one. It's fine. Okay. Two P and one P. Right? Or if you want, one integration and 0. If you put delta functions on the last integration, you kill the integration. Right? But what matters is that this relation is the real basis of, is the real fundamental relation for defining integrability in Heisenberg magnet with conformal symmetry, because it permits to build a universal transfer matrix, a universal R matrix, a solution of the Yang-Baxter equation that, unlike the Young R matrix, which is like so unlike the famous 1 plus UP, it doesn't act on a finite dimensional space. So we don't, we are not looking here at an RLL relation, the construction of a Lax operator, having a finite dimensional auxiliary space, but literally both auxiliary and physical space of the spin chain will be in a physical representation, if you want. So in an infinite dimensional representation, in the differential representation of the conformal group. And this R matrix takes the following form. Okay. So it is, on the operatorial level, is expressed via this operator. And its formulation is valid thanks to the validity of star triangle in any dimension. It's also valid for any space-time dimension. Okay. So here 1 and 2 are the linear spaces on which the R matrix is acting. Okay. And what are they? They are the space of representations of the conformal group defined by a certain scaling, delta 1 and delta 2. And, well, in general, this formula could be improved to representation that are non-trivial with respect to rotation. So we can put spins. We can, it's useful to work with symmetric traces tensor. So one could have an L1 and an L2, or in 4D, one could be more creative and L1 dot, L2 dot for having any left and right spin. So, but this is just a scalar definition. The same object exists, but let's keep it for the scalar. And this is a solution of the Yang-Baxter equation. So you see, it's an operator, is a solution of the Yang-Baxter equation built with integral operators, because these P square are integral operators. And therefore, it is actually, Yang-Baxter equation is actually an identity of Feynman diagrams. Okay. The kernel of R12 is this. Okay. Well, you see what I'm calling x12 square. So x12 square to the power alpha is, well, it's just multiplicative operator x12 square to the power alpha. And p square is defined also with a propagator which is integrated as a kernel. So product of xp px is a square of propagators, which is actually common object to see in vertex models in statistical mechanics. Nice. So the proof of the Yang-Baxter relation is simply, and this is really an exercise, is an iteration of star triangle moves on the medial lattice, which takes this, as an equality, it takes this form. Okay. The relation involves 3R matrices on the left and 3R matrices on the right of the equality, so R12 U minus V, R13 U, R23V is equal to R23V, R13U, R12 U minus V. Okay? So if this is R12, R13, R23 is equal to R23, R13, and R12. Okay? X1, X2, Y2, Y1, X3, Y3, X1, X2, X3, Y1, Y2, and Y3.
Can you obtain the finite dimensional auxiliary space as a limit of this general one?
This is a very good, this is a very interesting question. I would say not, it's not simple. No, I would say no. But what I know about this is in 2D, if you consider it 2D SL2C case, there are some cases where it was worked out how the R matrix reduced on the space of polynomials on Verma modules. So in that case, it's like some checks have been done, but is rather unexplored for what I know. I think it's very complicated. What I don't know, maybe to give a cleaner answer, is can I write R as a Yang R matrix, so the standard Yang R matrix as a split, with a split Casimir formulation in a differential representation in both, in the infinite dimensional representation in both spaces. Is it straightforward to do so, or to recognize that eventually this guy is really 1 plus u, like 1 plus u, first representation, first generator, second representation, second generator contracted? Is this R12 u for infinite dimensional representation? I'm not able to prove so. Okay, I'm not able to, but I'm limited, very limited. So. There is some piece of literature by Derkachov and others about Verma module reduction. How do you do fusion from finite dimensional representation to non-compact case? It's not just symmetrizing or anti-symmetrizing indices, right? So it's more complicated. A bit, well, you're gonna teach me. And yeah, that would be great. All right, well, there is an R matrix that solves the Yang-Baxter equation, so there is integrability, right? Because this allows to, at least to satisfy the naive definition of integrability, which is that we can write down independent integrals of motion, independent commuting charges for the chain. Now, if the chain has 1, 2, n sides, all of these sides, they will have a certain scaling dimension. Okay, so a certain representation of the conformal group. Then the object T as an operator acting on the tensor product of the sides, so on all the sides of the chain, and being specified by a choice of auxiliary representation by another scaling dimension is the convolution of integral R matrices which graphically takes this form. Convolution of kernels. So this is in the usual picture of probing physical spaces with an auxiliary space particle. This is space 1, space 2, and so on, space n, while here we are probing in the zero direction. This is the zero direction. And let's say that this point and this point are the same. So we assume, for instance, periodic boundary condition. The internal points are integrated, and T solves the RTT relation, which is a straightforward consequence of Yang-Baxter, if I define such an object. Sorry, let me call it 0, 0 prime. And therefore, the trace over the auxiliary space 0, which is the integration over the auxiliary space variable. Sorry? Yeah? Yeah, it exists.
You need inverse R matrix.
It exists. And is actually the same type of object. You just, you have some unitarity property by which R minus U is the inverse of RU. And the proof of that is also based on star triangulation. So every nice property that you would expect here, they're generally there, and their proof is a consequence of the braid, of that braid relation of star triangle. So RTT, if you have an inverse, which you do have, implies the commutation of the transfer matrices at different value of the spectral parameter, but now the expansion in the spectral parameter, the Taylor expansion and spectral parameter of these objects around a given point will produce all the conserved charges you can ask. Notice that differently from the setup where auxiliary space is finite dimensional, the expansion of this type of transfer matrix will not produce straight away, will not produce at all integral, local or multi-local differential operators, so differential operators acting on 2 neighboring sites or 3 neighboring sites and so on, but it will produce integral operators, so very non-local objects. There is a way to restore, at least at low order in the expansion, so in the linear order in U, something which is more familiar, taking the logarithmic derivative of this object. But then the map is pretty non-trivial. Okay.
But so why don't you use finite dimensional auxiliary space? It's like where everything is simple.
Well, I'm describing directly Feynman integral here. Okay. So I have a transfer matrix which is itself a Feynman integral, and I will use and I can prove everything by star triangle relation. If you want to use the finite dimensional auxiliary space, you are going to code in Mathematica very large matrices, use Lie algebra relation between the generator and show that these things are commuting, and then what? These are really the objects that I need to compute. Because if I know practically how to construct an eigenfunction of this object, and I will do it, generally speaking, at the level of the graph, so working with these integral kernels, well, I know precisely to diagonalize the Feynman integral. Okay, so the object I want to compute in the very end is not, it is a very non-trivial function of the charges of the of the spin chain, right? In general, what we want to compute is an observable of the spin chain is a function, can be non-trivial, of the charges of the spin chain, right? This function is very non-trivial if you consider the charges from RLL.
Well, the advantage is that normally in this way your conserved charges will be some integrated integration kernels, whereas if you start from finite dimensional, they will be differential operators, which is obviously nicer.
Yeah, but I can deal, at least for a certain set of computations that I have in mind, I can deal very easily with these integral kernels. And because I have the relation, this relation that it makes me do computation very quickly. I don't have to do anything in Mathematica or to prove that differential operators pass through each other or things like this, right? No. I will show you some example that if you are worried about the spectrum of the spin chain with periodic boundary condition, I agree with you that the two things should go together in the sense that I would look at the problem from the finite dimensional auxiliary space setup, but at the same time I want to know these objects because they may tell what are the analytic and asymptotics of the Baxter functions. And this is what happens in the 2D chain, which is relevant for Regge physics. Those T are almost the Q operators. So those operators that satisfy at the operatorial level Baxter equation with the finite dimensional transfer matrix. And if you have an explicit realization of this Q operator, you don't have to guess analyticity asymptotics. It's there, and you just have to read it out of the equation. For 2D, for 4D is an open problem. Yeah, there is a paper, but you know, you are one of the authors, I know. But come on, nobody has constructed this, the operators, the Q operators for 4D in this way. Or you disagree?
In 4D, I mean, this T become product of two Q functions, but there's not the Q functions which satisfy the fundamental Baxter equation. That's
yes.
Q is two indices, as you know.
Yes, but I agree, yes, but you're speaking about Q function. I would like to speak about Q operators, because that would allow me to have a first principle derivation of the solution. Because you need to know asymptotics and analyticity, right? So if you have the Q operator, you look at the kernel of these operators and you read what is asymptotics and poles. So that's what first principle means for me. Yeah, we may discuss this afternoon, I think. I'm not sure I understand fully those determinants in this sense. So.
Just one stuff. Maybe you said it and I lost it. This R matrix works just for the diagrams with two directions, or is working in general?
No, this is here D is general. You see, D is a parameter.
Yeah, okay. So you can have D, but just two direction in the
Excuse me. Yes. It's always just two directions in Yang-Baxter integrability. Otherwise, you would need some stronger integrability relation like tetrahedron equation. But that's
so this is related with the fact that you
really
were saying that with the three direction, for example, you cannot just
precisely the tetrahedron equation
okay.
could be a place to look at for understanding three direction, because you lift from the plane, so having squares, to tetrahedra in the space. But it's something yet to be explored. And in fact, a very interesting direction with respect to this Kagome I was describing before, which is not captured by this type of integrability. I don't know if the answer lies there, but it is tempting to look at it. Okay. So, right. Now, having described the general features of Yang-Baxter integrable Feynman integrals, and having defined the transfer matrix, integrable transfer matrix of a Heisenberg magnet associated to them, I'm going to give some example of field theory, which is described only by these classes of Feynman integrals. Okay? And therefore, since all the correlators will be described by integrable Feynman, by quantities that are ultimately observable of an integrable spin chain, the hope is to use, for various problems, integrability or separation of variable to solve the field theory. Okay. Right. Consider m slopes in the medial lattice, okay? And in fact, m equal to 2, 3 is already quite interesting. So if you have only 2 slopes or 3 slopes, the situation is already of different, it's much wider what you can do with 3 slopes, of course. Excuse me? The red. Yeah, I think I picked the same as before. Thank you. That works better somehow? All right. Okay. So with 2 slopes, all you can get is a square lattice. Okay. Which we really like because it looks like a collection of these R matrices. For 3 slopes, you can get more. You can get, for instance, vertex of valency 5, and then, yeah, maybe. Right, I could have chosen probably a better drawing, but let me see if I can. Yes. Well. Okay, the thing I wanted to show, and I didn't really manage well, by the choice of the lattice, which means I'm not copying from my notes, is that the valency, when you have 3 lines, 3 slopes, the valency of a vertex could be 3, 4, 5, and 6, whereas here it can be only 2. Okay? And if you increase the number of slopes, well, this is going to increase, right? You will have in general 2 slopes, valency 4, sorry, yeah, thank you. Okay. It's a very special case, the one of 2 slopes. You can only have 1. But in general, V goes from, in general number of slopes, you go from 3 to m. So you can have vertices from valency 3 to valency 2m. And then you can switch off some coupling, leave some couplings on, so you can put some extra constraint on what valencies you want to obtain. And in fact, you can play around with a lot of different. So the moduli space is quite large, and you can write down many different Lagrangian where you tune the interactions to the one you want, but constrained by the fact that you have a medial lattice. For m equal to 2,
Is there a relation between couplings, or you just introduce whatever you want?
Right. No, the couplings are not related. The couplings are not related. You are free to, so they are independent. They are independent, but what is true is that you will be able to relate always by moves of lines in the lattice. So by star triangle transformation, you can rewrite. For instance, if you have only three slopes, all the diagrams can be rearranged in such a way that are hexagonal lattices. Because you can put by star triangle relation, therefore, by producing some simple prefactor, you rearrange in a regular shape. Okay, this is possible in the bulk, of course, because then at the boundary, other things can happen. Okay, I did the opposite of what I promised. Instead of writing it as a hexagonal lattice of cubic interaction, I'm writing it as a dual object, in fact, which is a triangular lattice of valency 6 interaction. It's absolutely dual to it. They are the same thing, right? So there is a regular lattice structure behind. If you have 3 slopes or 2 slopes, but for 4 slopes, this is not true anymore. From 4 slopes on, you cannot be reorder things in this way. Okay. Now, for 2 slopes, let's write the Lagrangian, which is described only by this type of diagrams. Okay. So here, there are a few things that on the field theoretical side should be imposed. First, all these Feynman diagrams are planar, and in order to produce only planar objects, I need a matrix structure, so matrix indices for the fundamental fields, and define accordingly a planar limit. Secondly, I want all the vertices to be scale invariant, so there should be some dimensionless interaction, right? And yes, later I want to formulate their integrability. All right, and that's basically, yeah, I will illustrate that and then probably that's going to be enough for today. Okay, so the Lagrangian I want to write has a trace, because I need to have indeed matrix indices in the fundamental, in the fields of the theory. And the field of the theory I will call X and Y. X and Y have a scaling dimension delta X plus delta Y equal D over 2. For instance, for the isotropic situation is the standard scalar propagator. And the interaction is a quartic interaction. But due to the fact that these fields have indices, and actually, to be more precise, I will consider them to be adjoint in SUN. Why? Right. Thank you. Well, for the reason that these fields are complex and they are matrices, the Hermitian conjugate of this term is not equal to itself, and this is a chirality. It's what we call chirality. Okay. In general, in order to understand planarity, it's good to use the formalism of ribbon graphs. Okay, so one can visualize immediately if a Feynman diagram is leading or subleading when the number of color n goes to infinity. When this goes to infinity is what we call planar limit. And the theory I want to build should be described only by fishnets, which are planar, therefore in the planar limit. Planar limit is all what I'm caring about so far. So for SUN, the propagator can be drawn in this way. So this is the tensor indices, which satisfy the traceless condition for the fields x and x bar according to SUN, and this is the corresponding drawing. Okay, so contractions are given by lines. With this, with this formalism, one can indeed draw ribbon diagrams, and you see that the fundamental vertex is therefore this shape. Okay. So first of all, since this theory I promise that is somehow a toy model for n equals to 4, there are drawbacks here because I'm breaking unitarity. Okay, the Lagrangian is not Hermitian, so it's a non-unitary. Actually, it will be logarithmic conformal field theory, and conformal must be argued. There is no gauge field. See, there is no gauge field. So it's non-gauge, and it's also non-local. Whenever I'm in the general setup of delta x being from delta y, which I can also drop. I can make it local, for instance, in 4 dimension. Okay, 4 dimension I can make it local. Nevertheless, it is conformal at the quantum level. It is integrable, and it is a deformation of n equals to 4. So that's why it's not only a continuous spin lattice system with star triangle integrability, but it is also relevant in order to understand and test some techniques of n equals to 4. Okay, as a toy model. Ah, really? Ah, okay. Well, I thought the watch was was starting at 20, right? So now it's.
So it should be until 35, right? So I have 2 minutes.
Ah, we said okay. All right. So I'll wrap it up. Okay. I'll wrap it up just explaining how this Lagrangian appears from the deformation of n equals to 4. And the matter is the following. So you know in n equals to 4 there is some R charge symmetry. Okay. This SU4 has 3 Cartan. So to every field, to every elementary field of the theory, there are 3 associated Cartan charges. For instance, the field X will have 1, 0, 0. Field phi 1 alpha will have 1 alpha. Will have 1 alpha minus 1 alpha minus 1 alpha. The gauge field has zeros. So there is a way of deforming the Lagrangian, the action of n equals to 4, by deforming its commutator. So one replaces a commutator of 2 elementary fields, say phi 1 and phi 2, with a Q commutator. Okay, so Q phi 1 phi 2 minus 1 over Q phi 2 phi 1, where Q is a function of the Cartan charges of the 2 fields involved in this commutator, and is defined as follows. So you take the vector of Cartan charges, which I called C of the first field, transpose, times a matrix of twists, which is antisymmetric. Sorry, this is a log of Q, okay, which depends on phi 1 and phi 2, okay. So this makes a 3 parameters definition. So deformation, sorry. So the deformation depends on gamma 1, gamma 2, and gamma 3. And in particular, terms that will involve, for instance, the gauge field, you see immediately they are not deformed. Okay? They are not clearly not deformed because the vector of Cartan charges is 0. So if we push the parameter gamma 3, and it is a choice, it could be gamma 1 or gamma 2, to minus I infinity. So, yeah. And at the same time, the coupling of n equals to 4 goes to 0, such that there is a double scaling constant, which I call psi square. All the interactions in the theory are dropped, so they go to 0. For instance, A, because it is not deformed, so it will be subbleeding with respect to these terms. It will be killed by G going to 0. Or the anti-chiral vertex, so let's say yx, y bar, x bar. If the first goes with 2i gamma, the second will go 2 minus 2 I gamma, so it's explicitly suppressed by the large twist limit, and so on. So making this type of deformation both on commutator and on anti-commutator, what is left from n equals to 4 is really only this interaction. Okay. So a Lagrangian that in a planar limit is described uniquely by square lattices. Okay. So with this I'm done, and yeah, in the next this point in the next lecture we'll finish with the computation, with some conformal field theory computation. In this theory, I will show what do I mean by logarithmic field theory, and give you an example of computation for multi-point, multi-loop fishnet integrals on with this topology. Okay, that's it.
Can someone pass the mic all the way down the corner?
Yeah, so in the 2D case, the integrals you wrote look like closed string amplitudes. Would you still have an integral structure if you had the open string analog of that?
A string analog of this theory?
Yeah, so instead of integrating over all of 2D space, you integrate from one insertion to the next.
Yeah, no, I don't have. I never tried to integrate along the line these integrals. In fact.
Yeah, and maybe one more question. This Lagrangian is the unique one whose only Feynman diagrams are the integrable ones, or is just an example?
It's one example because this is the unique one if I choose to have two slopes, and therefore I fix this topology of integrable Feynman diagram. But I could do, as I was explaining, a plethora of theories where I can play with its moduli space, because increasing the number of slopes, I will increase the number of crossing between slopes, therefore of possible strength of the interaction, that is scaling power of the propagators that cross the intersection of slopes, and I will have different valency, therefore different number of propagators out of each vertex, even just for m equal to 3. So there is really a lot of theory that you can build, and all of them are described in the planar limit uniquely by integrable Feynman diagrams. What is nicer here is that we have a lattice structure, as well as for m equal to 3. There is a regular lattice structure. As soon as you switch on m equals to 4 and so on, you're going to lose that. The star triangle integrability should still be there.
Thank you.
Okay. Can I get one of the mics? Just to... Okay, before thanking Enrico, let me just, while I have everyone's attention, remember how